One of the common challenges we face in probability is to make computations efficient because although we're dealing with numbers that are between 0 and 1 in the form of probabilities, computing things can become quite cumbersome. So I like to call this the probability of at least. And that could be the probability of at least one thing, at least two things, etc. Occurring. So let's take a look at an event. Let's say our sample space is the set of all possible 10-digit bit strings. And so an example of this would be, like a 0, 1, 1, 1, 0, 1, 1, 1, 1, 1. Okay, that's 10 digits and that's a bit string. So a bit is a number between 0 and 1. And suppose that I want to know what's the probability, is the probability of randomly generating a 10-digit bit string and having at least one 1. Okay, now we know that that's probably going to be pretty high because there are only two possible bits for each digit. It's either a 0 or a 1. So if we were to randomly generate these, this is no different than a coin toss. It's like asking what's the probability that you toss a coin 10 times and that you get at least one head. So maybe we can even think about a 1 as being a head. Well, if we think about the sample space is going to be the set of all possible outcomes. And the set of all possible outcomes, if I were to sort of break this universe up into categories, here is the situation where I would have 0 ones. That's a possibility. I could have 1 1, probably not very likely, but these are events. I could end up having a 10-digit bit string that has 2 1s in it, or even 3 1s. Well, you get the idea. Well, what's the maximum number of 1s we can have? We can have up to 10 1s that we select at random from these different 10-digit bit strings. Now, if I want to know the probability of at least 1, well, that's going to be everything in here. That's going to be everything in here and here, and everything up to 10 1s altogether. So I could have basically 1 1, I could have 2 1s, 3 1s, all the way up to 10 1s, and I would satisfy the condition of at least 1. At least 1 means 1 or more. So what I would have to do is calculate the probability of getting 1 1. And as you might imagine, that's going to be actually a fairly difficult probability to compute. Maybe not impossible, but I have to think about all the different ways in which I could have exactly 1 1. So the one way would be to have 1 followed by a bunch of zeros. I could have 0 1 followed by a bunch of zeros. And I could just kind of keep pushing this 1 over one step. So there would be 10 ways in which I could do that. And these would all involve combinations, basically saying, okay, I have 10 slots, choose 2 1s to insert in there. How many ways can you do that? And I could calculate that, but I would be required to compute the probability of 10 different events, add them all together. So these are all individual events, and maybe I would call this E0 and E1 and E2, E3, and so on all the way up to E10. So the probability of having at least 1 1 would be the probability of E1 plus the probability of E2 plus all the way down to the probability of E10. That's going to require 10 computations, and then I have to add them all together. But another way I could think about this is that I know that the sample space is going to represent 100% of all possible outcomes. If you're looking at all 10-digit bit strings, then you could have as few as 0 1s or as many as 10 1s. And that's it. That's it. You can't have 11 1s or not, get negative 1s. That's the only set of possibilities. So if we look at all of the black rectangle here, and we want what's shaded in red, well, isn't that the same thing as just taking 1 minus and subtracting away the things that you don't want, well, I can say that this is the same thing as taking 1 minus the probability of E0. Okay, that would be the only, basically take away 100%, take 100% of all the possibilities and take away the percentage of those possibilities that do not correspond to what you want. Now, this could be the same thing for the probability of at least 1 or at least 2. Maybe we would have to add a couple of probabilities together and then subtract away from 1. But this would be a definitive way in order to solve that problem. Okay, so now I need to think about what the probability of getting 0 ones is. Well, the probability of getting 0 ones means I get all zeros, right? This would be all zeros. Now, what's the probability of getting that? Well, there's only one way to get all zeros. There's one way to have all zeros, and that's just by having a sequence of 10 zeros. We don't need to rearrange them because they're all zeros, they're all the same number, so there's one way to have all zeros. And how many possible 10-digit bit strings are there? Well, if there's, each bit has 2 possibilities, all the way up to the 10th possibility, and each of them has 2 possible avenues, well, that means that I could go one of 2 ways. I could say, well, here we go, we get a 0 or a 1 for the first bit, and then if we got a 1 way up here, then that could correspond to a 0 or a 1. And so you can see that these are just basically branches giving birth to other branches, and the first 2 branches will each give birth to 2 other branches. Well, this is just going to end up being 2 to the 10th power. So the probability of getting at least 1 is 1 minus the one way in which we could get no ones at all divided by the total number of possible bit strings we can create. You can imagine this can be pretty large, right? This can be pretty close to 100% because if you were to toss a coin 10 times, the likelihood that you would get all 10 tails is very unlikely. So this probability comes out to 1 minus, and this is going to be something really small. This number is 1 over 1024, which comes out to about 0.00098. And so if we subtract that away from 1, you can see that we're going to get 0.99902. So that means there's about a 99.902% chance that we get at least 1 in there. And that makes sense because if we're just randomly choosing 1s and 0s, then in all likelihood we're easily going to get that 1, 1. We're not going to get 10 ones very often, but definitely you can see that this just visually takes up way more space, the parts that are shaded in red, than the parts that are unshaded. And we could do the same thing, like I said, for if you wanted to know the probability of at least 2 ones, well then in that case, this region corresponding to 1, 1 wouldn't be shaded, so you would need to calculate the probability of this region and of this region, add them together, and subtract that from 1.